we're on for the second run of this show. Usually I expect people are not awake at this hour of the midnight. I'm not awake, so I've prepared a little bit of blather. We'll see how far we can go with the blather to keep ourselves awake. There's a reason for it. I say, first we obey the 7-minute rule. It used to be the 15-minute rule, but I'm rushing, so this is silly stuff. Wait for people to show up. Wait for the speaker to wake up. Things like that. Credentials. I've designed and built garbage collectors and memory management verbal strategies since before most of you were born. Sorry about that. It's awful. My dad used to say, it's no crime to grow old, but it sure is darn inconvenient. So, going through that phase. I often found that improvements in the garbage collector were like improvements of core amplifiers at down to the 50% level. Sometimes you got orders of magnitudes at algorithmic levels. I would say explicit knowledge about the program application domain. So that's going to be the theme of this talk. I'm going to try to focus in on what's really important to get you out of the groove, break the mold, and a few more aphorisms like that. Focus on lessons learned. Like fault analysis for GC. We've got a couple of these I want to show up today. And I've discovered a phrase that kind of describes the trouble of measuring G performance. I'm going to call it the flaw of averages, so keep that phrase in mind. Here's one of my 3.5 minutes worth of time wasters, but it does put in perspective what I want to talk about today. This concerns a story that actually took place at Columbia University. Joel Moses himself related it to me in good faith. Guy's defending his final thesis, and he's got his committee of 4. There's his thesis advisor, and the dean gets to make a selection, so he's given an applied mathematician instead of a mathematician. What a variety. The advisor selection, you get somebody smart, and the student gets to make a selection, get somebody few or somebody on the side. His thesis topic was mumble algebras. Beautiful, nice mathematical creation, had elegant theorems, concise theorems, provable, correct. That's what we look for, isn't it? I mean, a little beauty. Well, Dr. Skunk, the applied mathematician, really smells like an applied mathematician, to a pure mathematician. He asked him this question, well, tell me, if you had one of these mumble algebras, what would it look like? If you got a model, can we walk away to get a model? And during the final thesis defense, they walked themselves through a proof that the axioms of mumble algebra were inconsistent, and hence you could prove every statement. I got a shorter proof with your first theorem there, sir. Consistent, so kind of watch where you're going. Why are these skunk works things good? You know what I mean by skunk works? It's a phrase applied to World War II during a group that developed some fast aircraft, the Lockheed aircraft. They had to sort of break the mold of what corporate Lockheed was doing. They had this little building out in the middle of nowhere. They had no management structure, an outhouse away from others, and they could get something done. Creative. And especially that's true in software engineering research. You've got to critically re-examine what's important, break the mold, break free from what's provable or twice as fast or what everybody knows is true. And also, you have to achieve freedom from the flaw of averages. Here's my personal skunk note on my thesis proposal, qualifying jury. The dean's choice was a philosopher, and I was an applied mathematician. So I brought up my theorems on perceptrons, which was Marvin Minsky's idea of what AI might have been at that particular time. It was an interesting mathematical theory, and I had some really nice, elegant proofs, and I'm bringing up my first proof. And this Professor Grevin says, well, excuse me, Mr. White, before you go on with the rest of your theorem, presentation, I'd like to know just exactly why is it that your first important theorem is indeed important? And I answered, well, because it allows me to prove my second important theorem is a corollary. So you got to watch yourself about this, especially in coding and programming. You like to do that. You develop this stuff because it gets you to the next layer. Once you get to where this guy Columbia did, is you're at the end of something that's completely inconsistent, or in Silicon Valley, what's much worse, is unsellable. No more about that for now. I've got time to tell the third story too. The third story, again, is the same kind of approach to engineering that I'm trying to steer away from. 3 college students in the dorm. I had one of them, physicist, an engineer, and mathematician. And the fire breaks out in the middle of the night. Physicist wakes up, he sees the fire, he sees the fire extinguisher on the wall, and the dorm, he grabs it, just shoots the whole thing out, puts the fire out, goes back to bed. but there's a cause for the fire. It breaks out in another part of the dome. So the fire's again going. So this time it's the engineer who wakes up. He sees the fire, he sees it about this size, he sees the fire extinguisher. He says, yeah, it takes 3/4 of the fire extinguisher, puts out a measured amount, and puts the fire out. He's back to sleep. Wonderful. Yet the third time breaks out. This time it's the pure mathematician who wakes up. He sees the fire extinguisher in the capacity and says, there is a solution, and he goes back to sleep. This is a print of what was on the website. I'm going to deviate a little bit. I haven't put as much work into the details of areas. That's a particular management technique this is like to. I want to go over more of the history and make this like a perspective talk because there's a lot to learn by taking a broader perspective of memory management rather than just GC. Also, I have some slides that I'm probably not going to get to show today that go into the details of the so-called N-compler research that wound up with past numerical compilation from this. This work was done 30 years ago this year. It was published in 1973. It seems yet to have been reproduced in places where it ought to have been like in JonL. Okay, memory management from the very early days. This is your heritage. There was a machine called the IBM 650, the first commercially successful machine that wasn't expected to be successful, wasn't expected to be commercial. IBM built only 50 of it, then by demand they built thousands and made a lot of money. This was a huge machine. It was as big as a truck. It had 2,000 words of memory on a rotating magnetic drum. I wonder if we could put the slide up at this point. I wanted to show some hand-drawn slides that are going to have to be shown with the overhead projector here, but yeah, just turn it on and block out the PowerPoint presentation for a moment. Yeah, that's it. Hey, this was the first of this processor. Its memory structure was that it had a linked list of instructions. Why a linked list? Well, because the memory was on a rotating drum. It was not random access. You had to wait for the drum to come. Wait. It was like 50 milliseconds, which is 50 light years in modern day terminology. So you would try to link the instructions together so that after you finished executing one, the next one would be there ready and available. It's a nice, interesting technology. It's a lot of fun, right? But there's a lot of stories to tell about that I won't cover today. There are the channels, time going that direction, you're making your way through it. There was some AI program on that. That's where AI got its start on that machine. IPL5, Information Processing Language version 5, was implemented on the IBM 650. The famous professors Alan Newell, Herbert Simon, and Jay Shaw, Shaw's first name, had done that work at Carnegie. Undergraduates in the AI program tried to write actual computer programs and run them in IPL5, and invariably every single one would run into these two limits here. Not enough memory cells for a real problem. And even the most toy of problems that you can kind of pose in AI and try to put up in IPL5 would have memory leaks. Memory leaks. Ever hear of those? You ever use Windows? Well, okay, never heard of that. So Alan Perlis, who was the grand dragon at Carnegie in those days, discovered the need for a garbage collector in his language called formula alcohol. Briefly, formula alcohol was a reaction in 1962 to the work at MIT in the development of Lisp and the use of Lisp in artificial intelligence programs like Slagle's Symbolic Integration Program, SIN. So it was, CMU was playing number 2 in those days. We tried harder, and whatever MIT did, they could try harder to do. So it was an effort to try to do something that bypassed Lisp, but ultimately it failed. Perlis admitted that at the Lisp and Functional Programming Conference in 1982, which was held at the CMU campus. But nevertheless, both Lisp and formula alcohol and programs like that discovered we need an automated way because we simply are not going to waste the rest of our lives trying to get every last piece of memory management done by hand. Reminding us that John McCarthy at MIT did AI experiments first on the 650, and primarily after that on the IBM 704 and 709, Remember that Lisp had no compiler. It was a language. And Lisp had no compiler, no garbage collector at that time. Programs were hand translated from this meta language of square braces instead of the silly parentheses. Lots of terminally silly parentheses, that's how it got its name. And it was translated into Fortran and executed. By the way, I forgot to mention how we managed to get by in the 650 with 2,000 words of rotating magnetic drum memory. We really had to have some secondary memory. The secondary memory is basically where all the action took place. We used a kind of memory in those days called PPC. And often, for like compilers, I guess I'm not going to show this slide, because I'm going to show you one of these PPC cards. You're not going to believe it. This is how you do a compilation. In 2,000 words, you had a compiler, but the data structure, pass 2, pass 3, pass 4, would have to go out of this PPC memory. Nobody remembers exactly what it was. Well, you know, I had a terrible time finding an old JCL deck. You can't find these anymore, only in museums, punch paper cards. Every time you file a pass with a compiler, punching, IBM ranked up a few more cents in profit because you punch paper cards and just secondary memory. The irony. Garbage collection and our grandfathers that were in this technology, John McCarthy. By the way, I have a photographic, nice portrait of John McCarthy from 1998. What do we call this meeting? Lisp conference, ALU meeting, Bronze Developer Symposium, I can't think of it. He gave a keynote talk there. Now, he disavowed this story in later years. 15 years later, I approached him again and asked him about it. He claimed, I never said that, but he had. I was there. I took notes at the big lecture hall at MIT in 1970 when McCarthy came to talk on artificial intelligence. And he had a huge audience, people of all stripes, not just Vinci students and friends were there. And he waxed eloquent for about an hour or two on the history of Lisp as it stood in 1970. Now here's the interesting story. It concerned himself and a neophyte whom I think was Steve Russell, with someone recently told me they thought it was another one of the original pioneers. Took place in 58, 59, maybe as late as 60. It goes this way. The neophyte comes up and says, oh, it's all too hard, you know. This is Fortran. So all too hard, we have to make these 3 subroutine calls. What's a subroutine call? Procedure call. They're not thinking function, right? You just decided they call. You call subroutines and they decided that. We have to call allocate new cell. We have to call replace the car part. We have to call replace the footer part. Then we have to go grab out of a common variable or global variable this value. I mean, McCarthy agreed, yep, that's too much typing. And then the neophyte said, well, why couldn't we just define a function in Fortran? Define a function, do all that, and then return the address to the cell. Hey, that'd be pretty handy, wouldn't it? McCarthy said, well, that's a little bit big. But the neophyte starts to worry with it, but you know, we made it too easy to call const. What happens if we call const too much? At this, and probably begins to recall, because he's still thinking 2,000 words of rotating magnetic drum memory. I actually coded on that machine. I remember how I thought I'd mad for writing a program with 2,000 instructions in it. McCarthy looks at the guy and says, my good man, this new machine we're getting here, the 704, you can't possibly run out of memory. Why, this machine has 32,000 new cells. And the neophyte went away and finished. Remember that phrase back then. 32,000 cells. All right, setting the pattern again now, because we got back to the meat. I don't know if any of you remember the book by Gabriel on benchmarking Lisp systems. It came to a head around 83 or 84. In 1983, what was that conference called? Artificial Intelligence. AAAI, yes. AAAI in Washington. You were there. In 83, it was Washington.
No, it was Austin.
That was 82. Sorry, you're right. I remember. 82 was Austin. 82 was Washington. 83 was Austin. So this was the one in Austin, and then this Gitmo came out later. But there were a lot of questions on architecture techniques, Lisp performance, and so on. And as a result of that, it came up to this conclusion: no more GC papers unless. Because there were so many ideas, including my own, which was published in 1980. So many ideas were untested, sounded like nice ideas. They could have been like mobile algebras, you know. There is a solution, but they had to be researched. No more publishing without a working implementation of the garbage collector, no GC algorithm without benchmark numbers to show what you're talking about, and here's the important thing, no new benchmark numbers without believable explanatory theories. You see the difference there? You can lie with statistics, the flawed averages, you're going to see that later. You can lie with statistics, and if you get a theory, no matter how good it is, if you don't have statistics corroborated, we're not interested. All right, I think that's the end of this introductory collaborating session, which happily I won't consume 15 minutes on. Give me a moment, I'll find the other set of slides. How do I do this? Lost the page here. All right. Which one is that? I apologize if you're not having them on both on one slideshow. 9 seconds at a slide. No, not yet. There are 2 sets of slides, that's what the there. I did fail to merge them into one slideshow. Not very good. So, back to the question, what is memory management? And one possible definition is attempt to optimize the use of what is scarce. And that doesn't generalize too far. Most of you think memory cells are scarce. 30,000 new cells, that's a scarce thing, but actually addresses are scarce things in most worlds nowadays. Addresses and some more ideas of being scarce. Let's look at this historical progression of computer memory architecture, and we'll see how the focus of what we think is scarce changes as we go through the years. When you've got 10 to the third to 10 to the sixth addresses, 10 to the third, it's 1,000. Remember, 2,000 words of rotating around. They were successful, just like the engines run on the machines, big applications over there. We're effectively just attempting to recycle the use of addresses of memory, typical techniques, automated techniques in memory management, reference counting, market suite for ILC. That's completely satisfactory. You know, very fast, you see that way. It's not an architecture where you have 10 to the 7th to 10 to the 10th, say, something in that range. Then basically you're probably thinking of beginning to get into virtual memory. So the idea of compactifying your address space down into a smaller, swappable area is more prominent. Compactification as opposed to merely collecting the free cells becomes an important concept. If you're somewhere in the 10 to the 8th to 10 to the 12th number of data cells, compactification might even be out of question. Why? Because you could be distributed across so many pages it would take them now till the next century to actually touch all the pages and collect the one console from each mega page and get it compactified into your swapping area. So we're looking at something that goes by the rubric of generation scavenging, but basically what you want to do is only compactify the tip as opposed to the entire world. And by the way, you're not going to trace the entire world to find out how to compactify the tip of your growth. By tip, I mean things recently allocated. And finally, if you get into a situation of greater than 10 to the 12 addresses, which we are in, you've got to have something that's a little more radically different. In a paper in 1980 at that first, what we thought of as the first list conference ever, it was actually the second. The first was in 1964 in Mexico City. For us, the first one was at Stanford in 1980, and I presented a paper which went by two kinds of acronyms. One of them was garbage collection considered harmful. Don't do it. That is, take the techniques of memory management that don't force you into looking at garbage. An actual implementation of the ideas that were isomorphic to that appeared in the TI Explorer machine called the temporal garbage collector, somewhere in the mid-80s. Effectively, what that is hardware support to localize the working set, doing it on the fly. A little bit later, I'll talk about how that work is inspired by the Baker GC algorithm, which was focusing on the important part. But as I present the ideas, people come up to me and says, you know, hey, this is exactly what we're having to do with relational databases. So it's the same idea that relational databases are stored like huge disk farms, and somehow you got to swap into main memory, or swap into your paging area of your computer enough of the data from your databases so that you can actually carry out the structured query language hunts and other database activities. So it's a basic problem, very similar to databases. I haven't found a way to characterize it any better than that, but there's a relationship there. Now, one way to think of this is to compare it with the mathematical Lipschitz condition that says if you have arguments of a function that are close together, then the Lipschitz condition says, well, they're sort of proportionately close together in the range. Those things in the domain that are close, like the diameter of limited perceptron, right? If you're looking at this diameter here, you get that diameter there, you don't get the whole world. What's the domain? What's the range here? Well, the domain is things you constant recently, and the range is addresses that are locally compact. Nice relationship to have. Contrast these DDI temporal technique. Contrast that with the idea of good hashing schemes. And good hashing schemes, like CRC codes, YAML rings, things that are close together in the argument in the domain or argument space, are just scattered all over the universe. So there's your contrast. Second thoughts on our first generation techniques. Proliferate heaps by data type. DBOP, big bag of pages, so that we get a little bit more subdivided problem of garbage collection according to data types. Never mentioned it that way. It was done PDP-10 MacList at MIT by someone you know and see, and it was done quite independently. Barron and Newman, actually probably even 2 years earlier, by the likes of whom I don't know, but it was in the SDS 9 quarter list at roughly the same time as the PDP-10 MacList. It's an area. It's a memory management approach is still amenable to Markov suite with also extensions for contiguous arrays. Areas, the application-oriented areas. Somewhere in the mid-70s, those machine folks had this idea. Maybe it was Rudy Greenblatt presented it to me, but I think it was a broader idea that people caught on to. That you could get entire applications that would be stored locally and not scatter-loaded according to the way the memory manager might do it if you had a garbage collector. Store them locally that way that when you ran the new application inside this overall net, actually, put it this way, let's think of an application that's got 7 parts, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Sounds like a database, doesn't it? When you're working on London stuff, it's all local. It's not scattered all over the universe. So that's one of the approaches to areas. The second approach to areas is illustrated by the PDP-10 MacList approach here, was to have a pure space. Pure means read-only. There's a reason for that, because the operating system on PDP-10 in those days was homegrown at MIT. Always do the right thing. EPRT, do the right thing. The right thing was to have read-only areas where your code sat, the operating system sat, and non-immutable data sets so that you just didn't have to page it out. You know, and 3 different users on the machine would all be sharing the same read-only areas. It's a good idea. Your areas. Put that in the list. Make it a part of it. The next idea was called hunking. This was really containerization was a better idea. I've got a name for this. It's the idea that you're trying to pack things into a cargo ship, and every company's got its own jar size, its own package size, and some things only in common packages, and you just can't pack the stuff in. It's not possible. It just goes in as junk, and it occupies 5 pounds of junk occupies a whole cargo load. No way to get 50 pounds in. How do you get 50 pounds in? You put each item in a standardized container that packs well into the ship. Too bad if you don't fit in a standardized container. Take the next size larger. Waste a little bit of space in each container so that you can pack the ship solidly. And hunting does that with a waste maybe 20% of your area. Looking at various hunting schemes that I've implemented, and I see others independently. The ILC bug is implemented, you typically wind up wasting 20%. But if you've got a memory management scheme, then it does not get fragmented. And also, we have test case example of fragmentation in the worst possible way. And then reference down. This was done at Xerox Park, in Smalltalk, those B's, Cedar Mesa. That is a very big fix there to make reference down live like the difference. I think it's still a good, viable idea. And there is work going on in garbage collectors, memory management. There are even some guys at Microsoft who are doing it. Who knows if they're working on the Baker reaction. Around the mid-70s, Henry Baker, I guess, didn't like the idea of garbage collection on this machine. It had what I call my favorite kind of garbage collection. Don't do it. So you just ran for a couple of days, filled up your address space, then went home and rebooted, went out for a cup of coffee. It'd take all day or the next day to garbage collect and repack the space, and then you'd start over again. So having an incremental, real-time, independent process going while the mutator process is working and carrying on operations. Here's this Baker GC just moving stuff over on compacted binding. Anything accessible is moving on compacted binding. So you're in effect doing a stop and copy, but you're doing it live while you're actually thinking. And sort of somewhere along the way, you might actually find a case where you stop thinking for a little bit and really do have a complete image that's compact of your application. Well, there was a problem with that. Referred to it later as Declare's observation that you're thrashing, you're churning, you're taking stuff that's inherently accessible and totally worthless to you. I use the word poubelle thinking that it meant a little piece of useless garbage you don't need to look at, but it just means a trash can in Paris or something like that. But this poubelle stuff is getting churned in the activity of your machine along with all the data you're working with. Exposure down by an order of magnitude, that was the observation. That's why Declare would just turn his machine off. So there were reactions to the Baker GC. I mentioned a couple of them on this page, but the next page will be devoted to more reactions to how to fix it up. Unfortunately, I put myself ahead here. I shouldn't have. You would literally come first on the next page. But what's so important about this idea mentioned in the 1980 LISP conference, address memory management in a gigantic LISP environment or garbage collection has been harmful. It was an attempt to use this hardware-assisted copy. The thing that made the real-time garbage collector workable was it had a hardware assist. If the mutator process was trying to look at a cell, and the collector process was in the process of moving it, the hardware matched all up about it once a time. So that was pretty good stuff. We'll use those barriers that cause the hardware to match things up so that you can compactify stuff not willy-nilly, but as you need it. So if you try to reference something and it's not in your working set, then you swap it in. Hey, heard that idea before? It's called paging by page. Well, this is paging by object if you must. But the idea is that you wind up getting your objects locally compact if you're using, and then it would dynamically adapt. Hence, that's why the TI folks, I think, call it temporal GC, because it favors getting things that are temporally compact into things that are physically compact in memory space. Moon added a thing called ephemeral garbage collection. It was really a hardware-assisted substantial improvement. And they made the public assertion that real GC can't be done on stock hardware. Of course, the rest of us were stuck with stock hardware that weren't listed on or Xerox, Dandelions, or whatever, or symbolic machines. And I mentioned Texas Instruments implemented temporal GC. They didn't make reference to the 1980 paper in their patent proposal, but I don't think the proposal got approved either. In those days, it was hard to get anything software patented. These days, it seems to be hard to get anything of the software nature rejected because it just don't stand alone. Here's stock hardware responses to the Baker reaction. Remember, Baker's reaction was to don't do it, just run for 5 days, and then go take a paid time off day while the machine recollects things. So here's the secondary reactions. Generation scavenging garbage collection on stock hardware. Smalltalk's a good lead there, frankly. Peter Deutsch. Peter Deutsch was the father of the implementation, but also a father of Smalltalk implementation of stock hardware in 1982 at Park. Dave Patterson, professor, and under his graduate student at UCB, did it on stock hardware. And there was another reaction called conservative GC. This is taking a slightly independent domain of trying to apply GC to application areas like C code or C++ code where it is not possible to trace the stack because you cannot discern at runtime what's a pointer and what isn't. Whereas in the Lisp world or the Smalltalk world, perhaps to some degree in the Java world, you can always tell what's a pointer. So the garbage collector mechanical means no help. User to determine what's a pointer. Lucid took the plunge in '86, convinced by Alan Brock's experience with Smalltalk generation scattering garbage collectors on the MC68000 series machine. I think that by December '86, you finally began to read the handwriting on the wall. Yeah, maybe you could do this on stock hardware too. Not quite as efficiently, not quite as good, but stock hardware was speeding up. Park-based systems continued advancing those generational techniques until I would like to say quite recently. I think the way Bingo says, well, they continued advancing them until they didn't anymore. They went out of business. Like so many other places. Franz added a generation scaffolding garbage collection very close to the time that Lucid did, and had a flaw in it such that you didn't have a fallback, but we got the fallback implemented. I just don't remember the exact time frame, but that was a significant step because that garbage collector is, I've seen some details of it, having suffered under it recently at my current employer, and it's pretty complex, but it seems to be working now. Working very well for us. Harlequin took an approach that is one that I'm intending to foster, that there is no one single management technique that we know of that's going to be good enough. They offered a panoply they offered a toolkit called Memory Management Toolkit that had a whole panoply of ideas in it, and you could tailor it to your application need. It had a conservative component, if that's what you wanted. It had market sweep and reference counting. It was effectively a way of getting tools, and lightweight. I mean, it was pretty inintrusive. The ListWorks didn't use that. The ListWorks preceded the Memory Management Toolkit. It's unfortunate that when Harlequin died, that Memory Management Toolkit died with it. It had a park instead of Google, I think partly because there were some of those people on that history that didn't use it properly. You guys correct me?
It didn't die.
I'm sorry?
It didn't die. Great proposal for £1 is now open source.
Yes, and www.memorymanagement.org is owned by Ravenberg. Thank you. I'm trying to point you to that because that's where the remnants of the technology are as best I could find it by looking on the net. It's about a perspective, looking a long perspective. Things that are important. In 1969, large core memory cost about a byte per dollar. A byte per dollar. I know this is what multi-text memory cost back then. The first, the big real list was on multi-text back then. Well, it's before that, some stuff on our core. In 2002, reachable DRAM, PC-132 DRAM, cost about 10 megabytes per dollar. Catch the difference there? Between 1969 and 2002, we got 2 to the 5th years. But in terms of the decrease in price memory, is it like 2 to the 5th, or 2 to the 10th, or 2 to the 15th, or 2 to the 20th? I'm not sure where to stop there. From 1 byte to 10 megabytes at the same price. Okay, look at hard drives that we're using to back up main memory with now. Recent hard drives, as advertised in Dry Electronics, that was the American News, cost about a gigabyte per dollar. I used to say $1 a gigabyte, but no, gigabyte per dollar is the right way of saying it. Gigabyte per dollar. And the access and the throughput of these hard drives is faster than the main memory in 1969. You know, for a modest amount of a chunk of memory. Can you say orders of magnitude? Orders of magnitude, not 5, not 6, but more than that. Commerce One's business content, object-oriented aggregating database, iMerge. Well, it's changed the name from iMerge to something else, and who knows where some of this technology will go in the current recession. It originally started as a RAM resident database, and from processing about 1.2 gigs out of Windows, maybe close to 2 gigs out of Solaris. We saw a fatal limit for us. Even if we got 4 gigs, no, not 10 gigs. We're looking at business databases that go into the terabytes and no end to that. So ultimately, we wound up re-implementing a strategy where we're using RAM caching inside a gigabyte list to an SQL resident database. And we fell back on the 10 to 20 years of experience with people like Oracle and Microdata, Sybase and Ingress and so on to put into SQL database optimization. So we object embedding, rather flat object level, but object embedding, and it has worked tremendously well. Better than anything else that the conventional technologies questions are asked yourself. Why are we worrying about this small miss? You ought to have a gigabyte on your machine. You ought to have 8 gigabytes of, yes, gigabyte of memory. Don't you have a gigabyte at home? You ought to. Cost less than $100 nowadays. And you need it with Windows. Hey, you need memory management with Windows. Millennium, you have to reboot every couple of days. There's an accretion. In the San Jose Mercury News, the guru on Windows tells you, yes, because of this accretion of memory into Windows. Why should we ever pinch pennies again? Well, remember the neophyte who asked the question, what if you call save world too much? Oh my good man, you can't possibly call save world. This new info server has 32,000 gigabytes in it. And I'm not joking. 3 terabytes is sort of what we're contemplating in commercial applications, so 30 terabytes can't be thrown away. Taking a Python. Okay, I'm going to analyze one failure, then I'll be out of time. Taking a Python, you may have heard, or taking a snake. A failure in generations have in garbage collection, and then you just couldn't see for so long. The example here comes from the lucid optimizing Lisp compiler. It has a lot of rewrite rules that sort of rewriting and rewriting. It's an ideal candidate, right? Ideal candidate for generation scattering, because almost everything has a very short lifetime, and you're generating lots of it, so the numbers ought to look good. At the same time, one of the wizards at Lucid was performing experiments to analyze the compiler code and figure out where it could bounded extent applications. That is, instead of calling make foo, he would call dx make foo, where dx says, I'm going to make the foo, but I'm not going to constant the rate of heat. I'm going to constant in this temporary heat. And this temporary heat has a bounded extent in terms of time, where you start it and stop it, and at the end of time, you just throw it away. It's all done. No garbage collection. That's a nice thing. Constantly good heat, but when you're all done, it's all garbage. So you give it up and throw it away. Best garbage collection is no garbage collection. This clever handiwork I described, the guy who monitored and found that the way of building these techniques was Leonard Zutov. He built the tools to identify these places, to manage the overflow strategies for bounded extent allocation. Alas, Leonard died tragically in July of this year in a helicopter accident in Alaska. He had struck a ridge in the Linux world and was effectively retired at age 45 and was building his passion for helicopters. So, we're missing. He was for me, a very supportive colleague and a brilliant engineering coordinator. Never overlook the power of explicit knowledge over statistics. Explicit knowledge that you found these mechanical means tools to analyze the code and find out where to put bounded extent allocation instead of indefinite extent allocation. Now, not all allocations in this compiled phase could actually be proven to be in that extent, even though their average lifetime is extremely short. So again, this still ought to be a showcase for ETC to pick up the rest. Bounded extent allocation for most of the rewrite rules really made this compiler more than an order of magnitude faster. It was a savior there. But the fact is, we still needed the generation scattering for ephemeral garbage collection. But note well, although almost all consing takes place in an extent bounded by a function's contour. Start compiling the function, doing gigabytes consing, perhaps. Stop compiling the function when you're done, and it's all garbage. So that's the extent that we're looking at. Almost all consing, but it's not all. There's some things that are bounded by the compilation of the whole file, and of course, some things like recording proclamations in those, storing your desktop definitions, journaling things, and so on. However, in addition to generation scattering and garbage collection to the Lucid complex system, slows the compiler down like after fun. Come again? I think it's supposed to speed it up like I can slow it down. Why? All right, the fallacy laid the assumption that since almost no temporary objects survive to the end, then no large object will be clogging up the generation pipeline. That turned out to be wrong. It only takes one ever-growing large object, ever-growing, with a horizon time bound that's bounded somewhere, but you just haven't statically determined it. It just takes one of those to choke up your snake. It was the file global table for doing global literals optimization. That's in the top of the standard, right? When you can equify literals. That thing, there's no bound on it. How big is a file? Hey, it can be big. As long as the program writes it. How many literals is it? It can be big. You can make it as big as you want. There is no bound on that table. So the situation was such that even though everything, almost everything was being dribbled and dropped, this table was being swapped back and forth in the generations, the scaffolding growing without bound, until finally, just before the end of the file, the typical file, or the big file, just before the end of the file, the last scavenge took half of the entire compilation time. All the time you'd spent up to there, it was double again, doing that one last scavenge to copy that table over. And then you were done, and the table was garbage, too late, it's already in the tank space. That was the big right. What was the answer to that? Well, the answer was concept table at the beginning to make it big, explicit. Why a pig in a Python? I'm going to skip this slide because I do want you to see the last handwritten slide I've got there. It's a description of the flaw of averages. Looking at the bottom of this slide here, never overlook the power of explicit knowledge over statistics. Never overlook the power of specific knowledge over statistics. And see the power of explicit knowledge over the flaw of averages. Oh, boy, this thing is too big. Well, we have a pond here where the average depth is 3 feet. Average depth 3 feet. The 6 foot guy drowned. Why? Because there's a singularity that's 12 feet deep. And you look at the pond, statistically speaking, it's 3 feet, so how can you drown? Well, that's the flaw of averages. Explicit knowledge. Better to know where the crocodile is than where he isn't. Better to know where that hole is. And of course, that's what shippers do when they make charts of harbors. I've run out of time, but if somebody's got a quick slam at me, good. Everyone's